Hello students, let us start boost converter here. Okay, so here DC-DC converters are also known as choppers here. Okay, so the DC-DC converters can also be called as choppers. Okay, so here we will have a look at step-up chopper here or boost converter. You can name it as step-up chopper or boost converter, which increases the input voltage to a specified DC voltage. That means the output voltage is greater than the input voltage. Okay, so how this is happening here? So that means the output current will be less than the input current. Okay, so by changing the values of output current and output voltage, we are going to see the changes in the voltage. Okay, so if you want to increase the output voltage, you have to reduce the output current so that the power will be balanced. Okay, so that means the output power is increased, means the output current will be reduced. Okay, so that the power balance will be done. Now, so the boost converter output is greater than the input supply voltage, which is DC voltage. Okay, so let us see the circuit diagram for boost converter here. Okay, so here you can see this is the circuit diagram for boost converter or step up chopper. Right, here we have a DC voltage source Vs or Vi, and here we have connected an inductor, and here this is the switch here. We are going to keep the switch in between inductor and diode here, okay, parallel to the output supply. So this is your output terminal. Okay, you can connect any load. Let us connect a resistor load RL. So the voltage across this resistor will be our output voltage V0. Okay, so we are going to see what is happening in the circuit when the switch is on and when the switch is off. Okay, now let us see what is happening in the switch, what is happening in the circuit when switch is on. So this is the first condition we are talking about. So what is happening here when the switch is on? Okay, so here the switch is on means, so we are going to get the circuit like this. Switch is on means switch is closed circuit here. Okay, so here we can say the voltage source is connected to inductor and there is no voltage across the output here. Okay, so there will be no output voltage here. Okay, that means here diode will be in off position. Okay, and inductor will be having some magnetic field once it is connected to the source. That means this is the current here. Let us say IL. So IL will flow through the inductor. So due to this IL current, okay, when the switch is on, a magnetic field will be created around this inductor. So magnetic field will be developed. So this magnetic field will store some energy, that is energy stored in inductor, which is given by half L I square. Here this is IL. Okay, so some energy is being stored in the inductor when the switch is in on position. Okay, so now let us write down the expression for voltages here. So this will be the polarity for voltage across inductor. So these are the polarities for Vs. So I am writing KVL in the first loop here. So here what is happening here? The energy is being stored in the inductor. Okay, so that means the polarity of the inductor will be plus and minus VL here. Okay, so the current flow will be like this. Okay, this is the current flow here. Okay, so there is no current flow through the diode, so this is open circuited. Now the voltage across output terminal will also be 0. So okay, so while on condition, what is the voltage across output? So we are going to draw the graph here. So this is T on condition, this is T off period, and this is on condition. Okay, so while switch is on, there is no voltage across the output. So we are drawing the output voltage here. There is no voltage across the output, that is 0 here. But the current through inductor, this is IL here, current through inductor is increasing from 0 to T on here. Okay, so this is T on condition. This is T on condition. Okay, so as current through the inductor increases, the magnetic field will expand, that stores the energy here. So the terminal voltage will be plus or minus VL. So we are going to apply KVL here, that is minus Vs plus VL should be equal to 0. So that is Vs equal to VL, where VL is voltage across inductor. We know the expression for voltage across inductor. VL is voltage across inductor, that is VL equal to L into DIL by dt. Okay, so let us substitute this expression in our above expression. Okay, so that we are going to get the expression for inductor current while the switch is closed condition. Okay, so we are going to get Vs equal to L into DIL by dt. Okay, so I am going to find delta IL here. DIL is nothing but delta IL, which is equal to source voltage by inductor into delta T here. Okay, so delta T is nothing but change in time period, right? So that is, here the time is from 0 to T on. So delta T is equal to T on minus 0. So delta T can be replaced with on time period, that is T on here. So I am going to replace delta T with T on, that is T on. So this is current through inductor while switch is on. Okay, so we are going to find the current through inductor while switch is off period. So we are going to add them so that the sum of the current should be equal to 0. Then we are going to get the condition for output voltage and input voltage. Okay, so let us take this as equation 1 here. Okay, now while on condition there is no voltage across the output and current through the inductor is increasing linearly. Okay, actually it increases exponentially, but to represent it clearly we are keeping it linearly. Okay, now let us try to see the condition of the circuit when switch is off. So this is second condition, when switch is off. So when switch is off, what is the circuit behavior? So this will be the circuit. So when switch is off, the supply voltage will be connected to the output through the diode. Okay, so this will be the load resistor RL. Okay, so if you observe clearly, now we are observing some flow through the diode. Now initially there was energy stored in this inductor. Okay, so now this energy will be dissipated to the capacitor. This energy stored in the inductor in the form of magnetic field will be transferred to this capacitor here. Okay, so now the current will flow like this. Okay, the current flow will be like this. Okay, so the energy stored in the inductor will be transferred to the capacitor, but the terminals of the capacitor inductor will be changed here. Earlier they were like this. Now the inductor terminals will be changed to this one, because the current will be supplied by the inductor now. Okay, so that's why the polarity of the current leaving the inductor will be positive. Okay, so now let us apply KVL here. What is happening? The energy stored in the inductor is released and the current will charge the battery, will charge the capacitor, right? So if you apply KVL in this loop here, the current loop, so that will be minus Vs plus VL, sorry, minus VL, right? Minus VL plus V naught equal to 0. So if you observe clearly, what is the expression for V naught here? That will be Vs plus VL. That means what is the value of output voltage here? If Vs is 9 volts, let us say, if Vs is 9 volts and VL will be very high, that will be around 70 to 80 volts. Okay, so the sum of these two will give us output voltage. That's why the output voltage is maximum 79 volts, which is very much greater than the supply voltage or input voltage, right? So supply voltage is 9 volts, but the output voltage is 79 volts. Okay, this is how we are going to boost the voltage from input to output. Okay, the output voltage expression is V naught equal to sum of source voltage plus inductor voltage. In addition to source voltage, we are getting inductor voltage to the output. Okay, I hope you understand. Now let us substitute expression for VL. VL is L into DIL by dt here. Okay, here, so I am going to substitute VL in the above expression for output voltage, that will be V naught minus Vs equal to L into DIL by dt. Okay, so I am taking delta IL common, I'm writing it separately. That will be V0 minus Vs into delta t. Here what is the delta t here? Delta t is nothing but t off minus t on, right? Delta t is nothing but t off period, right? T off period is nothing but total t minus t on period. So what is total t here? T minus t on can be written as d into t. We have already seen this, so that will be 1 minus d into t. So t off can be written as 1 minus d into t here. Okay, t off can be written as 1 minus d into total time period. So that is what we are writing. So here the current through inductor while switch is off equal to V0 minus Vs by L into, here this is 1 minus d into t. This is nothing but t off period, right? Okay, so this is our second expression for inductor current when switch is off. Okay, so this is our second expression. So we know that the net charge through inductor, charge of inductor over one full cycle is 0. So for that we are going to add equation 1 and 2 and equate them to 0. So that will be Vs by L into T on, that is nothing but dt, plus V0 minus Vs by L into 1 minus d into t should be equal to 0. So by solving this expression, we are going to get the expression for output voltage, that is V supply voltage by 1 minus d, where d is duty ratio. This duty ratio can be varied by changing t on and t off values of time period. This is our duty ratio d.
So this is expression for average output voltage of a boost converter.
Boost converter or step up chopper. Okay, so let us do few problems so that you can understand it clearly. Okay, so here is the problem. A buck converter is given input voltage of 20 volts. The switch turn on and turn off periods are 30 milliseconds and 10 milliseconds respectively. Then find the average output voltage of the converter. Okay, so here we are given with given data. I am writing the given data first. So here the given converter is a buck converter. Okay, so what is the input voltage, supply voltage, that is 20 volts, and what are the T on and T off periods, that is T on is 30 milliseconds where T off is 10 milliseconds. Okay, so we need to find the output voltage. So to be found is output voltage of the buck converter. So what is the expression for output voltage of the buck converter? The average output voltage, I am writing shortcut, of buck converter or step down chopper is equal to V0 equal to duty cycle into supply voltage. So this is the expression we have derived in the earlier class, right? So we have supply voltage, but we need to derive the duty ratio here. Okay, so what is duty ratio here? Duty ratio is D equal to duty ratio which is equal to T on by T on plus T off. Okay, so T on given in the question is 30 milliseconds. Okay, T on is 30 milliseconds by 30 plus T off is 10 milliseconds. So we are going to get the expression for duty ratio as 30 by 40, which is equal to 3 by 4. Okay, so duty ratio is 3 by 4. Now we can find the average output voltage of buck converter. Which is equal to V0 equal to D into Vs, where D is 3 by 4. 3 by 4 into
4 5 is 15 volts. So output voltage is less than the input voltage. That is nothing but buck converter, right?
okay,
Because it is a buck converter
or step down chopper.
Okay, so let us take the same specifications and let us do the same for
boost converter. Okay, what can be the
questions? Okay, so we are going to consider
for boost converter. Okay, so detail for.
So what is the output expression for boost converter that is not equal to source voltage by 1 must be here. Okay, so here B is obtained, that is 3 by 4. Okay, so let us substitute the values here. Vs is 20 volts given. Okay, so by substituting these values, we are going to get the output voltage,
Average output voltage of boost converter. Okay, that will be V naught equal to source voltage by 1 minus T. Okay, so I'm going to substitute the values here. V naught equal to source voltage is 20 minus 1 by 3 by 4. So that will be around 20 into 4 by 1, right? 4 minus 3. So that will be 80 volts. So you can see that output voltage is 80 volts, which is greater than 20 volts, which is input voltage. That is because this is a step up chopper, step up or boost voltage,
increased output voltage
compared to the input voltage. Okay, so this is about buck and boost converters. Okay, thank you.